Right, so this is going to be about memory management in Python. And first, I'll explain the way memory works in this language, uh, what the global interpreter lock is, what it does, why it exists. Right, so first, we're going to look at variables and binding names to variables. So, one key point is that in Python, every single object is heap allocated. So, if you were to like imagine the memory, like the RAM, like your virtual memory. If you want to have a mental model of your virtual memory, you have your stack over here, which is going to grow downwards, right? So your stack is going this way. I don't have an arrow, unfortunately, to say that it's like going downwards. Um, anyways, and then the heap, which usually goes upwards, right? And here you have like other, like you're gonna have like with any executable, you're gonna have your block starting symbol, which is uh, data initialized to 0. Then you're gonna have um, like other data, which is like initialized to something else. And then you're gonna have your code. This is like your compiled code essentially, because when you're running the Python interpreter, you're gonna have your compiled code over here. So this is actually the Python interpreter compiled code. So then we have, whenever you declare a variable, let's say you declare something like, so every single object is heap allocated. What does that mean? Let's say we do something like x is 3, or no, let's do something else like x is something, right? And then do y is something. Well, what happens is that actually something, like the string something, essentially the bytes of the string, right? So every single byte of something is allocated here on the heap, and then x and y, they're going to be references or pointers, whatever you want to call them. They're just names uh, to the string something, right? So if you want a little demo to see the fact that's true, you can do, you can run this code. I meant ID. So ID gives you like the actual, the reference, or like the pointer. It gives you the memory address, right? So let's do demo1.py. So you can see they're essentially exactly the same. And this is also because Python has some sort of way of detecting that it can use that this something is already allocated. I have no idea how it does that actually. If I had to guess, it probably computes some sort of hash for this, and then whenever you create a new strings, it hashes it and it looks in some sort of internal dictionary to see if it has something. But that's just me guessing. If I had to. But anyways, you can see that they have the same address and they're essentially pointing to the exact same thing. So, uh, and this goes a little further if you want to look at something like, okay, so we also do something, um, so the Python interpreter also does something which is a little non-intuitive. I mean, very non-intuitive. I would say it actually starts like whenever you run up, like you run a script like Python 3 here, or you run a script. The moment the script starts up, um, what it's actually gonna do is it will uh, pre-allocate. So this is why I copied this. It will pre-allocate integers here. so it will pre-allocate some integers. I know, for example, it pre-allocates these like up to 256. So you can essentially think that they on the heap there's gonna be like some memory segments where these things are pre-allocated, and then if you do something like um, x is 1 here, what you're essentially gonna do is you're gonna take x. This is gonna be like again an address pointing to 1 on the heap, right? But the 1 was actually pre-allocated, and this is of course for optimization purposes. So if you do something like print the type of print the excuse me the ID of x, and y is 1 and the ID of y, they should also point to the same thing, right? So let's do right. So they point to the exact same thing, and you can see that actually, if this is to be interpreted as a memory address, which I think it is does ID in Python give a memory address? Implementation, this is the address of the object in memory, right? So you could do the hex of it. I mean, it's quite interesting that this is somewhere like B37428, and you can see that if you look at this, it's a much larger address. So they may even be stored in different segments. Um, should be right. Yeah. So this is definitely a heap address, but I think I was lying to you over here because this is not a heap address. I have no idea where this is stored. So if we were to think logically, this is a much smaller number. I mean, this is like um 11 million, and the other one is anyways, I don't know how to read this number. So it looks like the this one is, so the integers are probably somewhere up here, right? So these here are like really, I mean, here we should have like higher memory addresses. I have to think now. I didn't have to think before. Now I have to think because this is news to me, if you didn't realize that also. So, and here we have lower memory addresses, right? Because the stack grows downwards. So they're probably somewhere here. I would say they are before the stack, because they shouldn't be in the current frame of the stack. That wouldn't really make any sense, right? So yeah, just don't take everything you see for granted, and do a lot of experiments. Don't take everything you see for granted. But anyways, you can see that I actually point to the same thing. And one more thing is that if you do x is x plus 1, this is actually gonna, this means binding x to the object 2, right? So you're essentially doing the exact same thing. It's just x is going to be a reference to the object 2, which is already allocated somewhere. Right. We're also going to be talking about, let's move on to the global interpreter lock. So I'm going to write this out. Essentially what this is, a single OS thread can execute Python bytecode at a time. So what does this really mean? It means that the moment you're executing, like let's say you want to have, you would like to have two threads doing some computation in Python, you actually can't do that. Well, so if I would like to, I will write some code so I can exemplify this. let's say you have this Python code and you have it in a random function or like random computation, and you would like to be executing this on two threads. So execute these in two different threads at the same time. Well, you actually can't do that, right? That is not possible because essentially every single thread, so this is like general um, knowledge, so every thread has its stack frame, but so essentially you would have like two stack frames. You'd have like you can create two threads. I have no idea what the API looks like. Let's just say um create thread one, you give it that, and then so let's say you have some sort of API that creates two threads. This would create for you two stacks, two different stacks, right? And they both grow downward. They are probably one should come before the other, but I have no idea in which order. Probably that's implementation defined, if I had to guess, right? But they can't both be executing at the same time. So even though you have multiple CPU cores on your like processor, they can't be going at it at the same time because the interpreter, so the code in C, so C Python, what does C Python do? It does something like pthread mutex lock. So it essentially like it locks the it locks a mutex over here, and then it goes on executing Python code. So it just goes on executing Python code, and then it does pthread mutex unlock after it essentially gets out. And there are exceptions to that. Let's say that you have something like you use the library requests for fetching something. What that will do is inside of it, it will give up the GIL. So it will give up the GIL, and then essentially stack2 can just start okay, that's terrible. So then stack2 can start executing, right? So essentially the other function can start executing if you give up the GIL. So you can give up the GIL on things that are IO intensive, like doing library requests, because that so essentially this over here is going to go into a syscall. It will go into the kernel space, and from there it will essentially just be executing C code in kernel space in the TCP/IP stack, most likely waiting for the bytes to come back. And in the meantime, this other guy, right? So the other function can essentially pick up the lock, right? And this all happens in the text, of course, because that's where your Python interpreter compile code is, right? So this other function, it will pick up uh, the how would you say, it will pick up the global interpreter lock and it will start executing, right? And at one point it will give it up. It will see if this guy, but anyways, Python bytecode executes at most on one thread, right? Or no threads if you're like, if you don't, if you're an idiot, right? Okay, I think that's it's good enough.